The second example here has, again, three variables. X plus 2y minus 3z equals 2, 6x plus 3y minus 9z equals 6, 7x plus 14y minus 21z equals 13. So again, the first thing we have to do is to create our augmented matrix. And so here we have our three rows, my columns for the numbers and then the solutions. So 6, 3, negative 9 and 6, and 7, 14, negative 21, and 13. Notice in this matrix we're not missing any variables this time, so there's no zeros involved. We want this to look as close to the identity matrix as possible, so let's perform some row operations. I know that the 6 and the 7 have to turn into zeros, so my first row operation is going to be to set row 2 minus 6 times row 1. Since I'm not changing rows 1 or 3, I can rewrite them. So row 2 is 6 minus 6 times 1, which is 0. 3 minus 6 times 2, which is negative 9. Negative 9 minus 6 times negative 3, which is a positive 9, because negative 6 times negative 3 is positive 18. Negative 9 plus 18 is a positive 9. And 6 minus 6 times 2, 6 minus 12 is negative 6. But I still have to make sure this 7 turns into a 0. So my next row operation is row 3 minus 7 times row 1. Again, since I'm not changing some of these rows, I can rewrite them. So my next row operation, row 3 minus 7 times row 1. So 7 minus 7 is 0. 14 minus 7 times 2 is another 0. Negative 21 minus 7 times negative 3. 7 times negative 7 times negative 3 is a positive 21. Negative 21 plus 21 is 0. And 13 minus 7 times 2. 7 times 2 is 14. 13 minus 14 is negative 1. So here we have this matrix where we have an all zero row at the very bottom, but because your solutions column, the augmented column, has a negative 1 in it, this negative 1 makes this equation have no solution. Because the system of equations has this all zero row at the very, very bottom, we have no solution, but only because of that negative 1 in the last column. If it was a different number, it'd be a slightly different answer.